Good morning. Yesterday we covered the science of climate change, and today what I'd like to talk about is two of the most important regions in climate change, the Arctic and the Antarctic, the polar regions. Because these regions, not only does climate change affect them, but they radically affect climate change, and they make it worse. And we call this Arctic amplification. And so today let's discuss that. The Arctic and the Antarctic are going to change more than anywhere probably. And they're such rich areas. These, if you go to the Antarctic, this is a picture of penguins. I don't know how many penguins are there. There are king penguins on South Georgia Islands. This is a picture of my wife. And we were down there, and the penguins actually have paths going to and from the ocean. And my wife was standing there, and this little penguin waddles up and sort of stops and says, "Why is there this large red object in my path?" And she then went back and I told her to move, and she did. So anyway, we have a lot of wildlife and variety in the polar regions that are found nowhere else, and they're going to be affected. And we're going to talk about that tomorrow, the actual effect on the flora and fauna. Here's the main thing about the Antarctic. When light, visible light, falls on snow, it is reflected back. And when it's reflected back, it's still visible light. And so it goes right back out of the atmosphere through the same hole that it originally got in. However, if that snow melts, it's then brown, it's rock or it's water or something that will absorb the visible light. It is then re-emitted as not visible light, but infrared, and it gets trapped on the way out. And this is why we call it Arctic amplification, because originally that light was coming in and going back out. Now it's not, because of the snow and the ice that are melting. It is causing infrared, and as it goes out, it's being trapped, which causes much higher warming in the Arctic and the Antarctic. The other thing that's happening, if you look at the albedo change, now albedo is just a word for reflectivity. How is the reflectivity of the ice surface changing? NASA says that we are now reflecting more infrared than we did in 1979. And that total amount of energy that we are now absorbing here, rather than reflecting, is 100 petawatts a year. That amount of extra energy that we are absorbing in the Arctic is 7 times more energy in a year than humans use in a year because of the decrease in albedo. It's now rock and soil rather than snow and ice, and it gets harder and harder. This is just a graph of the Greenland ice sheet albedo. And you'll notice that in June and July it dropped down anyway. It melts, it gets water, it absorbs more. But look at what's happening every year. And you finally look at 2012, and 2012 was a catastrophe in the Arctic. We had more ice melt than anyone ever believed possible at this stage. We were predicting years and years before the ice melted, not after 2012. If you look from NASA at the surface temperature anomalies, what you'll find out here is that you look at how much the temperatures have gone up, and the most temperature change is happening in Antarctic, but not as much. The real serious temperature change is happening in the Arctic, and we'll get into the reason for that later. This is another look just from another temperature difference. This one's from NOAA, the U.S. National Oceanic and Atmospheric Administration. Look at the temperature changes in the polar area in the north. If you look at Greenland and you look at the extra energy that Greenland absorbed in 2011, just due to the change in reflectivity from the melting ice and snow, the amount that they absorbed was twice as much as the U.S. used in 2009, a huge increase. And that, of course, causes more ice and snow to melt, which further exacerbates the problem, and it's a downward spiral for the Arctic that is currently going on. Now, when the water melts, there's a couple things that can happen to it. It can run directly into the ocean, and it contributes to sea level rise. Or the water can form lakes. And when it forms a lake, water is a good absorber of visible light, and then it converts it to infrared. And so that makes the problem worse. Or, and this is a real problem, it can go down through the ice. And as it goes down through the ice, it gets underneath the glacier and it lubricates, and it allows the glacier to slide downhill faster going into the ocean. And if you look at this graph, these are two graphs that basically show the same things, but this is the total sea ice area. Now we got to worry about area, and we have to worry about volume. Area, of course, is just how much of the Arctic is covered, but that doesn't say where it's covered with ice 1/4 of an inch thick or 20 feet thick. But this is total sea ice area, and you see what happened in 2012. 2012 just fell off the cliff. If you then look at another graph of sea ice area, you can see where the ice used to be the normal, and you can see where the ice currently is. In fact, the Northwest Passage now, over through, from Alaska over to Canada, and from Russia over to Europe is now open. And in fact, there are now cruise ships venturing into this area and tankers, because it saves a substantial amount of time to go that way. This is a graph of what ice used to look like. In the 1970s, the total ice area in the Arctic was roughly the area of the United States minus our state of Ohio. If you want to look at it today, that's what it looks like. Gives you an idea. And keep in mind, every bit of ice that melts does not any longer reflect visible light. It turns it to infrared and causes the Arctic amplification. It causes it to get even warmer, which melts more ice in the downward spiral. This is just a graph here of Arctic sea ice extent. And of course, this is the winter, and this is the summer, but you can see what's happening. Not only has the ice been decreasing, but the percentage of old ice, in other words, a multi-year ice that's been there for a couple years, has fallen off the map. This is ice greater than 2 years old, and it's really down now to about 10% of the ice. Incidentally, if you want a good website on what's happening on ice, it's the National Snow and Ice Data Center. It's nsidc.org. Incidentally, on all of these slides that I have given you, the PowerPoint, if you want them, you're welcome to them. But at the notes area, underneath the PowerPoint slides, are tons of sites to websites and places that you can go to find more information on any of these topics. But the old ice is radically declining. Old ice, looking like this, reflects more sunlight. New ice tends to be flat, tends to melt on top, and that water absorbs. And so you will find out that new ice also is a problem compared to old ice. Now, satellite data now allows us to measure the height of ice above the water. And then, of course, you know that most of the ice is below the water, but if you know the height above, you can tell the height below. And this looks then at ice volume. And it's in volume that you'll find out that the bottom is falling off of ice in the Arctic. This is a graph of total ice volume here. And you look at where we are today. And then you look at this chart here. This says that in 1979, we had 16,855 cubic kilometers of ice in the Arctic. Today, we have 3,261. We have 1/5 of the ice in the Arctic than we did in 1979. And that is so exacerbating the problem of climate change, because all that energy that was reflected as visible light is now being reflected as infrared radiation and being captured on the way out. Now, this slide just is another graph of the sea ice volume. It shows you every single year, and you can see what has happened year by year by year, and it's getting lower and lower. This is the summer, this is the winter over here. Another problem is, as the ice melts, it obviously leaves open water. I've spent over a year of my life north of the Arctic Circle, and I can pretty much tell you that it doesn't snow in the winter. It's too cold to snow when it gets into January and February. It's 40 below zero. And so it doesn't snow. The snow, if there's old ice, this is summer, fall, winter, and spring. If there's old ice, the snow will fall on it, form a protective covering, and the next year that snow will reflect visible light away. If there's new ice, the snow falls into open water and it's lost, and it doesn't help to keep that protective covering that was there. So that's just another amplifying factor. If you look at the land, okay, in Greenland and in the northern Arctic, you'll find out that the April, May, and June, this is the snow cover from 1970 through 2010. Look at what's happening to snow cover in June when summer really gets started. We are just losing huge amounts of snow cover in the Arctic, which again now reflects infrared rather than visible light. There are a couple counterbalancing efforts at work, but they do not cause the amplification to in any way be hardly even slowed down. Because of the higher atmospheric moisture of 4% that we discussed yesterday, what we're finding out is we're getting more snow. But because of the higher temperatures, we're getting more snow melting, and so far the melting is winning on that one. Greenland has seen record ice melt in 2012. The surface melting in Greenland, one of the things you got to remember is Greenland's got a lot of mountains. I've spent a year in the northern part of Greenland, and it's so cold up there that even in the summer they don't melt. Well, not last summer. Last summer they were melting. It was so warm in the Arctic. And that, of course, is really causing sea level, et cetera, problems as it rises. And this is just from NASA, from the GRACE satellite, the Gravity Recovery Climate Experiment. And it shows that the ice melting in Greenland. Look at that number at the bottom. The total ice melt between September 2008 and 2012 was 367 billion tons. That's American tons, 2,000 pounds, but close to European tons. That's a huge amount of ice, of course, that is melted out of Greenland. And likewise, we're showing worldwide a huge decrease in marine terminating glaciers, a glacier that's actually coming right into the ocean. Both of these I took in Spitsbergen, Svalbard, whatever you want to call it, but they're glaciers that are coming right into the ocean. And we had a calving event in Greenland where that shows a glacier breaking off, and it was one of the largest ones ever as that glacier goes out to sea. A 100 square mile chunk of the Perlman Glacier. And we're going to see more and more events like that. And as this continues, we're seeing the water equivalent 340 billion tons of ice per year as the average change in glacier ice. Again, if you want to see numbers on this, go to nsidc.org. They've got really good stuff, but this shows you the average mass balance for ice every year. As this glacier ice is lost, it's going to cause a major problem worldwide. Now, this is not the Arctic or the Antarctic. This is worldwide because you have areas like Southeast Asia and India. If you look at the Himalayan mountains here, and you look at all the rivers, the Indus, the Ganges, the Irrawaddy, the Mekong, the Red, Yangtze, Yellow that come out of there, if we lose these glaciers, we're losing the water source for billions of people. And it's one of the things you got to realize, there's a big difference between runoff and rainfall and snowpack, et cetera. This happens to be the river, the numbers for the Colorado River where we live in Arizona. And every year, the Colorado River, the total rainfall was about 354 millimeters here. The evaporation, if you've ever been to Arizona, you'll understand why, is 309 millimeters. That leaves about 45 millimeters to actually run off and go down the Colorado River. But let's see what happens if you just have a 2% decrease in runoff and rainfall. And if you look, when you look at this one, a 2% change should be about 350 times that. So that's a decrease from 354 to 347. If you look at this one, a 309, that should be about 6. So evaporation goes from 309 to 315. But what that means then is that the total runoff is going from 45 to 32, a huge decrease. There are many studies that show that the Colorado River Basin, when they allocated the water among the states 20, 30 years ago, it was a period of very high rainfall for 30, 40 years. There are many studies that shows that the two large dams on the Colorado River could actually go to what's called dead pool within the decade, to where no water will get through them because the intakes are all above where the water is. And we're experiencing huge droughts, and the rainfall is constantly falling. Now, a huge problem in the glacier and in the Arctic areas is what's called black carbon. Black carbon comes from soot, it comes from burning dung and cook stoves, it comes from anything that's burning. When it falls on ice, of course, then it's black rather than white, and you get the Arctic amplification. And these emissions lead to radically decreased melting in the Arctic. Now, sea level rise is not only due to runoff, but the oceans are getting warmer, and so you have thermal expansion. Likewise, mining water from underground aquifers, once we get rid of it and use it, then it is dumped into the oceans also. And one of the key things to remember about climate change is, as the old saying goes, you ain't seen nothing yet. To melt ice takes 80 calories per gram. Currently, the oceans and the ice are acting as huge buffers. Over 90% of the heat generated by climate change is going into the oceans and the ice, not the atmosphere. But once this ice is gone, then it's got to go somewhere else, leaving only oceans. This is a graph from the Australians Meteorological Service that shows the amount of climate change going into the land and atmosphere, and this is oceans and ice, and you can see the huge area. This is a graph also from Australia that shows the mean average surface temperature of the ocean is going up. Now, we're going to discuss this in detail tomorrow when we look into what's happening in the polar regions. Now, the effect of the ocean's heating is very, very important in Antarctica, because there it's still really too cold to melt a lot of ice, but it's the oceans are now melting glaciers from underneath, and they're melting the ice caps from underneath, and then the currents carry the cold water away and bring more new warm water in. And as the sea ice disappears, it loses its buttressing effect. If you consider a channel and the ice is hooked fully to the shore, then the ice above it can't push out. But once you lose that, the ice can easily slide down. Also, if you look in the Arctic is getting greener, and this is a normalized difference vegetation index from NOAA. It looks at vegetation, and what you'll find out is this whole area around the Arctic here is getting greener, and that also absorbs more energy. And it's a new CO2 sink. We're actually taking some CO2 out of the atmosphere for that. And a problem up there as it's getting greener is you're getting things like larch pines. And larch pines are perfectly nice trees, but they don't lose their leaves in the winter. And as soon as spring comes up, the sun starts shining. Instead of falling on snow, it falls on pine leaves, and that further exacerbates warming. Vastly more sunlight is now going into the ocean, and this is causing algae blooms. Nature abhors a vacuum, and if there's any extra energy around, something's going to take care of it. So you are getting algae blooms. And that, of course, will help some species, and it'll hurt some species. There are always winners and losers in any climate change, and the question is who will come out on top in the end. And another thing about the ice is the ice buffers the heat transfer from the oceans to the atmosphere. When there's ice there, you do not get the heat transfer. But if the ice is not there, you get heat transfer from the oceans to the atmosphere, warming the atmosphere. And we talked earlier about the polar cell. And the polar regions stay very cold in the winter because A, there's no sun to heat them up, but B, there's an ice buffer to keep the energy coming up from the ocean. Now in Antarctica, of course, there's no ocean. There's mountains, so that stays even colder. The important thing to realize there is the polar cell is decreasing. If you look at what's called the North Atlantic Oscillation, which is the difference in pressure between, say, Bermuda and up and around Iceland and things. That's radically changing. The polar jet stream, if this is a very low pressure up here, which it is if there's ice and there's no heat, then the jet stream will circle around up here. But as this warms up and that effect lessens, the jet stream is dropping down into here. And when that happens, and the jet stream drops way down, we get polar air. A lot of people say, what do you mean climate change? Have you looked outside in Arizona? It got down to 20-some degrees. A couple years ago, it got down to 18. What's happening is the jet stream is dropping way down because it's not being held in by the low area around the polar. So we are going to see a lot more freezes if the jet stream, a couple years ago, it dropped down over Europe, and they were absolutely record-setting temperatures, even for Moscow, but as far south as Paris and London, they were getting incredibly low temperatures due to this effect, that the jet stream is not held tightly to the pole. A huge worry is what's called methane clathrate. A clathrate is any substance where you have a molecule that has a structure, and trapped inside that structure, like this is ice and so forth, trapped inside that structure are methane molecules. And if the methane is trapped inside here, it can't get out. But what if that ice melts? And what we're finding is that we now believe that the methane in the clathrates is between 500 and 2,500 billion tons of carbon. We think the total natural gas resources in the world are 230 gigatons. So it's a huge amount of carbon. And as that starts melting, this is actually a picture of ice burning. It's clathrate ice that's burning. As that starts melting from the permafrost, as the permafrost melts, you can release huge amounts of methane. Methane is a much better, if you want, greenhouse gas than carbon dioxide. And so what you will see then is just a runaway, a more exacerbated greenhouse effect from the methane that is coming out. So we are going to put huge amount of methane into the air as this permafrost melts, and it looks like it's going to melt. It's certainly headed that way. Let's look at Antarctica. Now there's a difference between Antarctica and the Arctic. The Arctic is land and there's ocean, so it's ocean surrounded by land. Antarctica is land surrounded by ocean. And that makes a difference, because obviously the land isn't going to melt. In the winter you still have land there, and even in the summer you have land there. The Antarctic Peninsula, though, which is this area here pointing up sort of towards South America, is one of the most fastest warming places on the whole Earth. This part of Antarctica, it's warming a little, but again, it's high and it's so cold that even with warming, you're not seeing that much snow melt. So in that part, you're not seeing the runaway effect of Arctic amplification like you are in the Arctic, but you certainly are down here. And the mountains are so high, as I said, that in many areas it's not melting yet. But once we start getting warmer and warmer, it will. And new snowfall has a higher reflectivity, so we're getting more water vapor, we are getting more snow. That's helping to keep the Antarctic cooler. And we aren't getting the feedback effect that we are. So with that, thank you. And tomorrow we're going to look at what this Arctic amplification is doing to the wildlife in the Antarctic, because that's not a pretty picture. With that, thank you. I'd be happy to answer any questions.